All right, class. Um, Good afternoon. Uh, I apologize for starting my lessons a little bit late today. Um, hey, Rourke. I on Wednesdays and Sundays I do a more intense run, and so I knew I was going to be a little bit tired and slow to start. And then I cut my hair too. I don't know if you can tell. Let's see, who do we got today? Hey, Rowan. Hey, Christian. Hey, Zach. Hey, Justin. Hey, Alex. Hey, Alex. Hey, Mina. Um, so, can you see Hazel? There's Hazel. I had her positioned so that she was off to the side, but she wanted to be behind me. All right. So, what we're going to be talking about today, this is going to be a really easy lesson, so I wasn't worried about starting 5 minutes late because it's going to be super easy. We are talking about what is called a transformer. Hey Aisha, no, that is not Bug barking. That is a neighbor's dog. So we are talking about transformers today. So let me show you what a transformer looks like. You have some wires that basically make an inductor or a solenoid, like that. And then you have another wire over here, like that. Okay. Now, this. Oops, someone else said hi. Hi, Adam. This coil right here is called the primary coil of the transformer. And this coil right here is called the secondary coil. And hey, James. The primary and the secondary coil are going to have different numbers of turns. Okay, so the primary has, I'll say, n sub p turns, and the secondary has n sub s turns. The way I've drawn it, it looks like n sub s is greater than n sub p. Okay, and these two coils are connected via a piece of iron. So there's a piece of iron that goes from one coil to the other. Okay? So this is iron. Now, we talked about how iron has the effect of enhancing magnetic fields because it has a large permeability. So let's suppose that you have a certain input voltage. So there's, and I'm going to use this symbol for the input voltage. So there's an input voltage. Well, that voltage is going to produce a current that goes through this coil. Okay, so there will be a current that goes in. And that current, when it goes through this thing, you might remember that this is called a solenoid. And when current goes through a solenoid, it creates a magnetic field. So the primary coil is basically acting like a solenoid. Okay? Now, the purpose of the iron, so that this solenoid is making a magnetic field. Now, what the iron does is it guides the magnetic field into the secondary coil. Okay? So normally what happens is if you have a solenoid, it just makes a standard magnetic field pattern. But if you have a piece of iron, the magnetic field likes to stay in the iron. It doesn't like to leave the iron. So it will sort of guide the magnetic field into here. So basically, the primary coil is creating a magnetic field, and that magnetic field is fed into the secondary. Okay, and then the secondary, because this symbol right here means an AC source, so it's a voltage that is changing sinusoidally. So because the voltage is changing sinusoidally, the current is changing sinusoidally, which means the magnetic field is changing sinusoidally. So you have a magnetic field that is changing for the secondary coil, which is going to induce a voltage, according to Faraday's law of induction. So there's going to be, if you put a resistor here, it's going to experience a voltage, which I'll call V out. Okay? And it turns out that V out over V in equals the number of turns in the secondary divided by the number of turns in the primary. So basically what a transformer has the effect of doing is it has the effect of changing the voltage from one level to another level. Okay? Okay? So for example, so let's do an example. What if the primary has 50 turns and the secondary has, let's say, 900 turns? Okay? And we'll say, what is the output voltage if the input voltage is equal to, let's say, 10 volts. Okay? No, Zach asked the question, does there need to be a resistor on the secondary side? No, but then you're not using the voltage produced by the transformer. So, okay, so you would have V out over V in. V in is 10 equals 900 over 50, which is 18. Okay, so it's the ratio of the two turns. Okay, and then we multiply both sides by 10, so we would have V out equals 180 volts. So what the transformer had the effect of doing was turning 10 volts into 180 volts. So we would say so basically you can, so Christian asks, so basically you can carry current without the wires being directly connected. Yes, so there's no wires connecting this circuit to that circuit, but one circuit is affecting the other. Yeah, through Faraday's law of induction. So because the voltage went up in this case, this is called a step-up transformer. Because the voltage increased. Okay. If the voltage goes down, it is called a step down transformer. Okay, so you have step up transformers and step down transformers. I want to make a comment. Transformers Justin asked a really good question. I'm going to get to that in a second. Transformers only work with AC circuits. Okay? Transformers only work with AC circuits. This is one of the reasons why our electrical grid is based on AC. Because if we look here at the secondary coil, the only reason the secondary coil has a voltage is because of Faraday's law of induction, and Faraday's law of induction requires a changing magnetic field. Okay, so we have to have changing values for these quantities in order to get the induced voltage at the output. Okay, so you're only going to get transformers to work with AC circuits. All right, and because it's useful to be able to change the voltage level, this is one of the reasons why our power grid is based on AC. A second comment. Every step up transformer can also be a step down transformer. So how does that work? Well, if we look at this, if we took this transformer and we just turned it upside down, then the secondary would become the primary and the primary would become the secondary. So the ratio would flip. And so in this case, it multiplied the voltage by 18. If we flipped this transformer upside down, it would then divide the voltage by 18. So you can take a transformer and you can turn it around. Okay. Transformers are usually heavy because they have this iron section. So transformers are typically going to be fairly heavy. Okay. Now I want to get to Justin's question, which was, doesn't that mean if the voltage gets stepped up, does that mean that there's no energy, or that energy is being created out of nothing? And basically, a transformer is just a piece of iron and some wires. There's no sources of energy in a transformer. So a transformer cannot create energy. Okay? So basically, the power that goes into the transformer has to equal the power that goes out of the transformer. Okay? Otherwise, that would mean that the transformer is adding energy into the circuit, but it doesn't do that because it's, it's just a lump of iron. Okay? And remember, the formula for power in circuits is I times V. So the current that goes in times the voltage that goes in has to equal the current that goes out times the voltage that goes out. Okay. So I can take this and I can multiply stuff around, and so what I would get is I out over I in. So current out divided by current in is going to be equal to voltage in divided by voltage out, which is number of turns in the primary divided by number of turns in the secondary. So what this says, you'll notice, is that this is the opposite ratio. See how for the voltage it's NS over NP, but for the current it's NP over NS. So what that means is that if you have a transformer like this one, where the voltage was multiplied by 18, then the current is going to be divided by 18 in order to conserve energy. Okay, so you don't get something for nothing with a transformer. It just basically what a transformer will allow you to do is it will allow you to change the voltage at the expense of lowering the current, okay? Or lower the voltage if you need more current. So Christian asked a great question, which is how are transformers used? And you might recall that I talked about because P equals I squared R, this is the formula for the power dissipated by a resistor. We want to have as small of a current as possible when we're transmitting power, okay? So if you're transmitting power over great distances, you have these long wires that are carrying electric current. And because they're such long wires, they have substantial resistance. So what you want to do because you don't want these wires to be dissipating power, that's just waste, right? If you're transmitting power over 100 miles and some of that power is being dissipated by the 100-mile long wire, then it's just going to heat up the wires and it doesn't do anything for anybody. So we want the power that is lost during transmission to be as small as possible, which means we want to transmit our power with the lowest possible current. Okay, but we still want to transmit the same amount, a lot of power. So P equals IV, right? So if we have to choose a small amount of current, but we still want to transmit a lot of power, we better have a really big voltage. So power is transmitted with incredibly high voltages, 100,000 volts, 200,000 volts, etc. And the reason that they do that is so that the current can be low. Okay, so basically what happens is you have, if you're transmitting power, you have a power plant. Okay, and then the power plant produces, a certain voltage. Okay, but it's not a large enough voltage to avoid the losses caused by this I squared R losses. So what you do is you then feed the output of the power plant into a step-up transformer. Okay, so now the voltage goes up to 100,000 volts, 100 kilovolts. And then what you do, so this wire right here, this is the wire that goes from wherever the power plant is all the way close to your house, okay? And then somewhere close to your house, there's a power station where there's a step-down transformer. Okay. And the step-down takes the 100 kilovolts, and there might be multiple step-down transformers, so it might happen in stages. But eventually there's going to be a step-down transformer that steps down the voltage to 120 volts RMS, which is when it's going to go directly into your house. Okay. So you use transformers to adjust the voltage so that you can transmit power efficiently. So yeah. Apparently with modern technology, they are able to step up and step down the voltage with DC. But, this was the first way we learned how to do it. And so that's what our electrical grid is based on. So yeah. All right, well, that's my lesson for today. Me and Hazel are signing off. Hope you have a good day. One more thing I wanted to say is, so there's been a lot of conversation about that email that went out regarding student grades and whether. So it looks like probably what's going to happen is your grade can't go down from March 13th, which is the last day of school, that we were in school. Alex has asked the question, how do you step up or step down voltage with DC? I know it involves semiconductor technology, and it's not something. I invite you to figure it out and tell me how it works, because I've never looked up how it works before. But anyways, regarding the grades, it's looking like probably your grades are safe. I don't know, that the email that they sent out was just really unclear, and everyone's confused right now. All right, I'm signing off. Have a great day. Bye.